Hello everyone, my name is Andrew Jones and I'm one of the LAs for Computer Engineering 331 at Penn State. I wanted to make a quick note / hint / tips video for LAB1, as in the past I've seen students struggle with understanding exactly what the lab is asking and how to go about implementing the restoring divider. So, first thing I want to note is make sure that you're on the correct version of Avado. If you should be on version 2020.1 or 2020.2. If you're on 2020.3 or 2020.1.1, you won't see the correct project part that we need for the labs and the final project, so make sure you switch over to that version as soon as possible. If you're using the W205 lab computers, it should be on version 2020.1, so you don't need to worry about that. For this lab, you're creating this circuit shown here. This here represents a restoring divider. This here is the same as shown in the lab doc. I've just highlighted a few things that I wanted to point out. More details on exactly how the restoring divider actually divides is shown in parts 2 and parts 3 of the LAB1 doc. You will make two main modules in your lab, a divider module and a test bench module. These modules should be implemented in separate files, and your divider module can be composed of smaller submodules, also in separate files. This isn't required, but I highly recommend that you use these submodules for your code instead of doing everything in one divider module. More on this later. Your divider module will have the following inputs: A, B, clock, clear, and start. A will be 32 bits wide, B will be 16 bits wide, and clock, clear, and start will all be 1 bit wide. Your divider module will have the following outputs: Q, R, ready, busy, and counter. Q will be 32 bits wide, R will be 16 bits wide, ready and busy will be 1 bit wide, and counter will be 5 bits wide. Your divider module should have the same functionality described as in parts 2 through 4 in the lab document. Another thing I want to note is that you don't have to use these exact names for your inputs, but you should name them similarly. Your test bench module will not have any inputs or outputs. Your test bench module should instantiate the divider module and assign the correct inputs and outputs to it. You will also need to generate the correct signals to send to the divider module within an initial block and an always block. These correct signals are shown here. I'm going to real quick go through all these signals and what they are and what they should be. A and B should be these hexadecimal values. These values will not change during simulation time. Clock will start as 1 and it will swap its state every 5 nanoseconds. Clear and start will start off at 0. 5 nanoseconds in, both of them will go to 1. Clear at this point will stay 1 throughout the rest of the simulation time. At 15 nanoseconds, start will go back to 0 from 1, and it will stay at 0 for the rest of simulation time. I'm now going to describe to you a sample divider module. This is how I recommend that you should implement your restoring divider. You don't have to follow this exact layout in your Verilog code, but the behavior and outputs of your code should be the same. Your divider will use a few internal wires and registers for the computation. All of these, except for busy, ready, and counter, are shown on the diagram. That's this diagram here. For the registers, I recommend that you call them reg-B, reg-Q, and reg-R. This is what they're named in the diagram. I use camel case, they use snake case, you use whichever case you prefer. It's up to you. We won't have separate Q and R wires, as these are unnecessary. We can just use the output values of reg-Q and reg-R. So basically, this Q is just going to be reg-Q and this R is just going to be reg-R. We're not going to implement these as two separate wires. If we want these values, we can just use reg-R and reg-Q. For your subtractor, I recommend you call the output wire subtractor out. For the multiplexer right after the subtractor, I recommend calling the output wire submux out. And for the multiplexer right above reg-Q, I recommend calling the output wire aqmux out. To go through on the chart, this here, the output of this should be sub out, the output of this should be submux out, and the output of this should be aqmux out. If you want to use different names than what I've just said, you can do that, that's completely fine. Just make sure it's clear what each wire and register is. Don't use ambiguous terms like mux1, mux2, reg1, reg2, etc. All of your internal registers, which are busy, ready, reg-B, reg-Q, reg-R, and counter, will all be assigned on the positive edge of the clock within an always block. Inside of your always block, you'll assign register values based on the following conditions. When clear is 0, all of your registers are going to be set to 0. When start is 1, register B is going to be set to the value of the input B. That's this on the diagram. Register B is going to be set to this B value here. Register Q is going to be set to its appropriate multiplexer output. which is going to be the output of this multiplexer here. Register R, ready, and counter are all going to be set to 0, and busy is going to be set to 1. When busy is 1, register Q and register R are going to be set to their appropriate multiplexer outputs. So register R is going to be set to the output of submux out, and register Q is going to be set to the output of AQ mux out. Your counter is going to increment by 1, so counter equals counter plus 1. If the counter is 31, that means that after this computation we will have the correct result for our division. So we'll set busy to 0 and ready to 1 to indicate that we're no longer executing a division operation and that the output of Q and R are valid outputs. I've decided to give you all a little bit of code from the implementation I described above. This should hopefully help you get started on the rest of the assignment. This code here represents our subtractor module. It takes in two inputs, A and B, and an output, register S. All of the inputs and outputs are 17 bits wide, which is represented as 16 through 0. This module is fairly simple. We have an always block that triggers on any signal change, represented by this @ here. This always block will set the output value S to the input values of A minus the input values of B. This here performs our subtraction operation. This here is the sample code for the divider module. Some parts of this are incomplete. For example, we don't have submux and AQ mux declared in here, as well as the modules and wires for them. And we also don't have the conditions for when start is 1 and when busy is 1 inside of our always at pause edge clock block. This is up to you to implement. At the top of the module here, we have all of the inputs and outputs we described earlier. We have clock, clear, start, A, B as inputs, and then regQ, regR, busy, ready, and counter as outputs. We have our internal register regB. As in our diagram, we take the input of B and assign its value to register B if we're in the start equals 1 block. Our subtractor module is declared here, where we take the inputs subtractor A and subtractor B, and then the output subout. These three wires are declared up here. We'll note that the subtractor A and subtractor V values are defined as concatenations. The subtractor A value is defined as the concatenation of register R and the 31st bit of register Q. Remember that register R is 16 bits wide, and 31st bit of register Q is just 1 bit, so concatenating these together will give us a 17-bit value. For subtractor B, we are concatenating a 0 represented by 1 binary bit, and the 16 bits in register B. This gives us a 17-bit value. Subtractor out is also defined as a 17-bit value. Subtractor's out's value is not defined here, as it is set in the output of subtractor here. Your subtractor mux and your AQ mux would be declared around here. I recommend that you use the same approach I did above for declaring the different inputs and outputs for it, as well as for actually defining the module itself. Now we'll start talking about our always block. Our always block, unlike our subtractor, which executes at any signal change, will only execute at the positive edge of the clock. This means when the clock goes from low to high. Inside of our always block, we have an if statement followed by two else ifs. In our first one, we define that if clear equals 0, then we take all of the registers and we set them to 0. Note that we're using non-blocking assignments here. This means that all of these will be executed sequentially instead of executing regB, then regQ, then regR, etc. These will all be executed simultaneously. We also have the conditions here for when else if start equals 1 and else if busy equals 1. However, the implementations of those are left blank. These are up for you to do. Some extra advice that I give all of you is that I highly recommend that you look over the Verilog slides regardless of when you took or how well you did in CMPEN 270. Specifically, you'll really want to know the following information. I recommend that you go through all of the lectures and slides, but these are some of the points that I think are most important. Lecture 1, slides 61 through 64, which talks about wires, assigned statements, which is structural Verilog. Lecture 1, slides 65 through 72, talks about modules and module instances. Lecture 1, slide 75, talks about concatenation. We talked a little bit about that in our sample code. Lecture 1, slide 76, talked about representing numbers in Verilog. We talked a little bit about that in our concatenation for subtractor B. Lecture 2, slides 7 through 15, talks about structural versus behavior Verilog, plus the intro to behavior Verilog, which is always blocks. Lecture 2, slides 16 through 32, talks about procedural code and blocking versus non-blocking statements, which is effectively what you do in an always block. Lecture 2, slide 37, talks more about edge triggering, which is the same pos edge clock, neg edge clock, etc. Lecture 3 talks more about things that'll be more important in labs 3 through 5 in the final project, but I highly recommend that you look through Lecture 3 anyways if you have time, and at least before you do Lab 3. This concludes the notes/hints/tips video for Lab 1. Hopefully this video gave you a better idea of what's expected in Lab 1. If you're still unsure about Lab 1, I highly recommend that you come to office hours or email any of the TAs or LAs in the course. The emails and the times of office hours can be found in the syllabus. Have a great day.